What is the physical interpretation of the Duhamel's principle? As you know, this principle is a very interesting strategy to solve non-homogeneous ordinary differential equations or partial differential equations. This idea tells us that you can convert a non-homogeneous equation, partial differential equation, with the homogeneous initial conditions to a homogeneous equation with the non-homogeneous initial conditions. The Duhamel's principle is a generalized form of the variation of parameters, which is a very interesting tool to solve the ordinary differential equations, non-homogeneous form. Okay, let's start from the heat equation. As you see, we have a source term in the right-hand side of the equation, but the initial condition is homogeneous. First of all, I have to solve this equation, which is homogeneous, but this time the initial condition is non-homogeneous, and the source term appears in the initial condition. This is so strange. How is it possible? What is the relation between the source of the heat equation and the initial condition of another equation without the source term? And also here, as you see, I have the initial condition at time eta. So this is at time 0, but this is at time eta. And then this is so straightforward to find the solution, or to transform the solution of this equation to the 0, to time equals 0, and the solution of the original equation equals the integral of this solution from 0 to t and d eta. So you vary the position of this eta from 0 to the final time, and t is the time at which the unknown function should be computed. Okay, the proof of this relation, the mathematical proof, is so straightforward. Suppose that you don't have this relation, but you have the idea of finding a homogeneous equation. This is so difficult, extraordinary more difficult. But at my current position, I have the chance to have the solution, so I can just replace this relation in the equation and check if both signs are equal. So, for the mathematical proof, compute the time derivative of this integral, and then find a second derivative of this integral with respect to x, and then combine these two derivatives. If the result equals f, so this integral solves the original equation. This is the time derivative of the result. Pay attention that you have to use the Leibniz rule, because the derivative is with respect to t, and the integration contains t in the upper limit. So this is the Leibniz integration rule, the derivative of integral. And the second one is the derivative with respect to x. So you can simply interchange the order of integration and derivation. And here you have to use this differential equation and replace the second derivative of w with respect to x. The result is the negative of this integral. So when you add these two derivatives, these two terms will cancel out, and the only remaining term is the first term. And if you look at the initial condition of the second equation, the value of w when eta equals t is equal to f of x and t. So this the second side of this equation will be f of x and t. And also check the initial condition, the value of u at time t equals 0 equals the integration from 0 to 0, which is obviously 0. Okay, let's start the second part of my today's lecture, which is about the physical interpretation of this strange and magical mathematical theorem. Okay, so let's start from the wave equation. And this is a string, for example, a vibrating string. An external force is exerted on this string. And the variation of an exertion of this force will change the velocity of this string from time t to time t plus delta t. Delta t is the time interval, and when you exert a force on a system, obviously based on the second law of Newton, the velocity will change and the system will accelerate or decelerate based on the direction of the force. So the velocity will change with respect to time from v to v plus delta v. V is the velocity of this system. I'm trying to prove that the Duhamel's principle is nothing more than the conservation of momentum, or the second law of Newton, and the conservation of energy in the heat equation. Okay, so when you F over m, F equals ma, F over m equals a is the acceleration, F over m equals f. So, and a equals the derivative of velocity with respect to time. So, in a finite interval, the change of velocity equals the f times the change of t, or the time interval, or the time step size. So delta v over delta t equals f, and let's use the dimensional analysis and try to find the dimension of w here. This is the original wave equation, and this one is the second equation, which is homogeneous. So this is the homogeneous wave equation, and the initial conditions, and the second initial condition will change, and you will replace the 0 in the second initial condition with f. So, and this is wt, which is the time derivative of w. And let's compute the dimension of w. This is a simple physical relation or mathematical relation, and the dimension of both sides should be identical based on the dimensional homogeneity, and consequently the dimension of w should be the product of the dimension of f and t, which is time in our case. And also from the original equation, the dimension of f equals the dimension of the second time derivative of u. U is the displacement of this string. So the dimension of u over the dimension of t squared times t. So the dimension of w is the dimension of u over the dimension of t, which is equivalent to the dimension of velocity, because u is the displacement of different points of this string. So w is something like velocity, is a kind of velocity. So I can write delta u, or the variation of the position of different points on the string, equal w times delta eta. Eta is a time-like coordinate. And also from the Newton's second law, velocity, the time derivative of velocity, which is acceleration, equals the value of the force exerted on the system at time eta. And also w is velocity, so the time derivative of velocity equals the time derivative of w at time eta equals f at time eta. This is exactly the second initial condition in the converted, or in the second partial differential equation. So I have to solve this equation using these initial conditions, and after computing W, you can easily integrate this relation, and you will find out that U equals the integral of W over eta from the initial time to the final time, which is t. So you solve another partial differential equation in a period of time from 0 to t, and you combine these solution using the integral. This is the result of linearity of the original equation, and to construct the solution of the original equation. Okay, let's investigate the physical interpretation of the Duhamel's principle in the heat equation. This is again our system, and this time F denotes the amount of heat added to the system, and here I have to use the first law of thermodynamics, or the conservation of energy, or the energy balance equation. As you know from your basic knowledge of physics, when you add a magnitude of heat to a system, the temperature of that system will increase. The product of the mass of the system and the heat capacity and the temperature change, U here it denotes the temperature. The temperature change should be equal to the added heat. Q is the rate of heat. So the product of Q and the time interval equals the added heat, which should be equal to the product of MC and delta U. This is the simple form of the conservation of energy. So F times delta T equals delta U, or the change of temperature. Based on the dimensional analysis again, because I'm trying to find a physical interpretation for a purely mathematical tool, so I have to use the dimensional analysis as the first step to convert a purely mathematical relation to a purely physical relation. Okay, so here again, based on this relation, initial condition, the dimension of W equals the dimension of F. So both of them have identical dimensions. But using, and also F, based on the original equation, the dimension of F equals the dimension of U over the dimension of T. And consequently, W is something equal to or equivalent to the rate of change of U, exactly similar to what we found in the wave equation. As you see, W is equal to the rate of change of U. U here is the displacement of the string, but U in the heat equation denotes the temperature of different points. Okay, so delta U equals F delta T, and delta U over delta T equals F. So F is something similar to the rate of change of temperature. When you add heat to a system, the temperature would change, will change with time. Exactly similar to the situation when you exert a force on a system, the velocity will change. So the final equations are similar. Delta V over delta T equals F here. Delta U over delta T equals F. U is the temperature, V is the velocity. So W is something proportional to the change of U with respect to time. And again, F is based on the conservation of energy equals the change of temperature with respect to time. So F at time eta should be equal to W at time eta. And this is the only initial condition in the converted homogeneous equation. And also delta u equals w delta eta, because f is something similar to w, and so you can replace f here with w, and this if you integrate this relation and also decrease the length of the time interval, so the integral appears, and u, which is the solution of the original equation, equals the integral of the w over time from the initial time to the final time.